Humans have come very far in every aspect of technology, from creating small fires with stones to creating big fire with bombs. But one of the most useful technological inventions humans have ever done are computers. The first ever computer was created by Charles Babbage in around 1830s, which was not an electrical but a mechanical computer. It was also called the analytical engine, and was powerful enough to perform simple arithmetic calculation. Ever since, different types of computers have been invented, like an analog computer, the digital computer we use today, and the hybrid of the two. But in recent years, a new type of computer, also known as quantum computer, have been gaining popularity, claiming to be a new and superior form of computing. So in this video I'm going to talk about quantum computers, explain how they work and are they really a superior form of computing as compared to modern-day computer. But first I'm going to talk a little about how classical computers work, so you can get an overview of how in general computers work. So the classical computers computes every computational information in the form of bits, which are referred to as 0 and 1. Now 0 and 1 are not actual numbers. 0 and 1 actually represent the passage of electric current through the terminals of logic gate. When the electric current is not passing, it represents 0, and when it's passing, it represents 1. These logic gates are made from some bunch of transistors, and a bunch of these logic gates together make a computational machine, which can do basic arithmetic operations. Now talking about quantum computers. Quantum computer computes information in the form of quantum bits, in short qubits. Now because it's an animated video, I will be using different colored spheres to represent a qubit. But mostly for representing the character of qubit I will use the yellow colored sphere. Now coming back to the main topic, the notation 0 and 1 is also used for representing the state of a qubit. Physically, for a qubit, 0 and 1 refers to the orientation or spin of the qubit. Qubit has an up and down spin. If the up is chosen as 0, then the down is chosen as 1, or vice versa. Now as you may know, that quantum particles are very, very small, and according to quantum mechanics, particle plus very, very small equals strange behavior, and this strange behavior is known as the quantum superposition. Most people think of quantum superposition as being all the states at the same time. Due to this misunderstanding, people think quantum computer computes everything parallelly, or at the same time. This myth of quantum parallelism is mostly spread by news articles. Most people understand this as if bit can only be 0 or 1 at a time, but a qubit can be both 0 and 1 at a time. That means a bit can only represent one piece of information at a time, but a qubit can represent two pieces of information at a time. Thus, to bits equals to pieces of information, but to qubits equals 4 pieces of information at a time. Thus, for 3 bits, 3 pieces of information, but for 3 qubits, 8 pieces of information, and so on. And that's how quantum computers are proven to be parallel computers. But I must tell you that quantum computers use a really different form of computation. To understand this, you really need to understand what quantum superposition is. Let there be a quantum particle, and it can have two types of physical states. The one is the classical state, and the other is the quantum state. Let's suppose the quantum particle have 3 different classical states. Let those classical states be the red-colored sphere, the green-colored sphere, and the blue-colored sphere. Its quantum states also has a color, but we don't know what it is, because we can't see or measure the quantum state of a quantum particle. If we try to do so, the quantum particle will only let us see one of its classical state. Because it's a fundamental property of the quantum particle, we can't do anything about it, but we still want to know the color of the quantum state. So let's try to figure it out with a small experiment. Let there be 3 machines, and let's name them red machine, green machine, and the blue machine. The red classical state can enter and pass through red machine. The blue and green states can enter and pass through blue and green machines respectively, but none can pass through machines which doesn't match their color. Now if I pass the quantum state of a quantum particle through each machine one at a time, it passes through every machine with the color that was supposed to be coming out from that machine. Now let there be an RGB color machine, through which all 3 color state red, blue and green can pass. Now if the quantum state of the quantum particle enters the RGB color machine, it also passes through the RGB machine, but obviously not in its quantum state, rather in one of its classical state. But the interesting thing here is that the classical state, in which it comes out is completely random and probabilistic. Now you would be like, yeah, okay, that's cool, but we yet still don't know what's the color of that quantum state of the quantum particle. What's the point of this experiment? This experiment tells us about the random and probabilistic behavior of the quantum particle. On the basis of this random behavior of the quantum particle, we use a mathematical trick to represent the color of the quantum state of the quantum particle. We mathematically represent it as though it's in a superposition of all three classical states. This complex mathematical mixture is known as the quantum wave function of the quantum particle, which is actually represented by Greek letter psi. In this wave function, the classical states of the quantum particle are treated as vectors in a vector space, and these coefficients are just some complex numbers. Graphically, the quantum wave function of a quantum particle would look something like this. These peaks and downs are due to the complex coefficients of each classical state, but a quantum wave function doesn't represent anything physically. But if we take a square modulus of it, we get a probability density distribution over a state space for all its classical states. This probability density distribution simply tells us in which classical color or state the quantum particle is most likely to collapse into when being measured. As you can see, it has equal chances of collapsing in each classical state. Now if I were to be asked, what is the color of the quantum state? I would say the color of the quantum state is 33.3% red, 33.3% blue, and 33.3% green, but it doesn't mean it's in all three colors at once. It's a one single color or state. You can consider it just like how a particular combination of color red, green, and blue can give a completely unique color, but it doesn't mean it's in all three colors at once. It's a one unique color. The only difference here is that we can measure the result of the combination of the elements, because these are actual colors. Whereas in the case of quantum mechanics we can't do the same thing. We only get to measure one of the elements of the quantum mixture. In short, quantum states are not multiple states at the same time. They are also single states. It's just that we can't measure them, so the most accurate way to represent them is mathematically on the basis of the classical states that we can actually measure. Now if the quantum states are also single states after all, then what gives quantum computer the quantum speed up, and what makes them different? The answer to that is, just like how there can be unique infinite possible resulting colors, by just changing the proportion of the constituent colors, there can be infinite possible unique quantum states. By just changing the probabilistic amplitudes, as long as the modulus square of C1, C2 and C3 add up to 1, because they are probabilities and probabilities always add up to 1. The quantum computer's job here is to increase the probability of the outcome of a specific classical state through all these unique quantum states. This can be done by constructive and destructive interference of quantum states. This is a property of waves, which is also shown by quantum particles. The states leading to the wrong answer interfere destructively, hence decreasing the probability of the outcome of the wrong answer, and states leading to the desired answer interfere constructively, hence increasing the probability of the outcome of the desired answer. In summary, quantum computing is all about creating a pattern of constructive and destructive interference of qubits. That increases the probability of desired outcome. So if there is a bomb that is about to explode, it has 5 wires and only one of them is the correct one, then the probability that the correct wire will be cut is 1 by 5. The quantum computer's job here is to increase the probability of cutting the correct wire by constructive and destructive interference of qubits, so that the bomb has less chances of explosion. You can somewhat say quantum computers as a kind of parallel computers, if you want to explain it to a 5-year-old. But what's actually happening is the constructive and destructive interference of quantum states. Now let's discuss what kind of real-world problems a fault-tolerant quantum computer will be able to solve, and how better and efficiently will it be able to solve as compared to a classical computer. I am going to discuss 3 most popular problems, which have been argued that a fully fault-tolerant quantum computer will be able to solve. The first problem on the list is large integer factorization. For people who don't know, when we send any type of information through our electronic devices, it's first encoded into product of 2 very large prime numbers. Let's call them P and Q. Their product is itself a very large number, which is around 617-digit long. To give you an idea how large this number is, the number that will represent the number of atoms in the universe is around 82 to 84 digits long, which is still around 533 to 535 digits less than the product of P and Q. This method of converting plain text into ciphertext is known as enscription. When the message reaches its location, it is then decoded back to plain text from ciphertext by converting the 617-digit number back to its 2 prime factors P and Q. This process is known as description. This is achieved by using the product key, which contains the value of P and Q. But if an intruder wants to gain unauthorized access to the information in the message, he has to do so without the product key, which means he has to iterate through all the possible factors of the product until it gets the value of P and Q. But a 617-digit number would have so many possible factors that it would take more than 1 billion years even for today's most powerful supercomputer to find P and Q. A quantum computer will be able to factorize such a large number in just a matter of days by using the quantum algorithm known as Shor's algorithm. Thus, quantum computer will break our ID security by making our modern encryption and decryption method useless. But they may also introduce a new method of encryption and decryption, which could be more safe and unbreakable as compared to our modern encryption and decryption. But let's not discuss that topic in this video. The second problem on the list is searching through large and organized databases. Suppose there is a person who likes to collect physical copies of all the video games he plays. He has built a huge shelf just for storing his video games. The games starting with the letter A and B are stored in the 2 sections of the first column. The games starting with the letter C and D are stored in the 2 sections of the second column. The games starting with the letter E and F are stored in the 2 sections of the third column. The games are stored in this way up to the last column, which contains the games of letter Y and Z as their first letter. This shelf is an example of an organized database. In an organized database, all the data is stored in a particular order or manner. Here the shelf is the database and video games are its data, which are stored in an alphabetical order. If the person wants to pick a video game, he can do so by just following the first letter of that video game in the shelf. The person doesn't need to look through the whole shelf. But if all the video games instead of alphabetical order are stored in a completely random order, this shelf is now an example of an unorganized database. In an unorganized database, all the data is stored in a completely random order. Now if the person wants to pick a video game, he doesn't have a choice other than to iterate through all the video games in the shelf until he finds the video game he wants to play. He asks his friend Classical Computer for help. Suppose it takes a single computational step per video game for a classical computer, and there are n number of video games in the shelf. Then it would take at most n amount of computational steps to find the video game the person wants. But if the person asks his another friend Quantum Computer, the quantum computer would find the video game in just square root of the number of computational steps that classical computer took. In summary, if the classical computer takes n number of computational steps to search through an unorganized database, then a quantum computer would take square root of the number of computational steps that the classical computer took to search through the same unorganized database. The third and the last problem on the list, but not the least, is the quantum simulation. This problem led to the idea and development of quantum computers. Due to the vast complexity of quantum mechanics, many problems in physics remains poorly understood, like low-temperature physics and many-body physics. Even modern-day supercomputer becomes inadequate to simulate quantum systems. With just 20 quantum particles, it is interpreted that a quantum computer will be able to simulate quantum particles very accurately, due to the fact that it directly exploits the properties of the real quantum particles. If it is able to do so, then many problems that require deep study and understanding of behavior of quantum particles will be able to be solved. For example, quantum simulation could help in the field of medicine. By simulating the behavior of certain types of molecules, it can help in finding a potential cure for some certain incurable diseases. It may also help in design and discovery of new drugs much faster than the hit and trial method we use today. Quantum simulation could also help in the betterment of the environment by allowing us to study certain chemical reactions more accurately. For example, it can help us make fertilizers in a much more environmental friendly and energy efficient way as compared to how we make these fertilizers today. The main ingredient for making fertilizers is nitric acid, and the key component for making nitric acid is ammonia. To make ammonia, the bond between the nitrogen atom has to be broken. But doing so is not easy, as it is one of the strongest chemical bonds. This process of converting nitrogen gas into ammonia is called nitrogen fixation. So in modern day, the industrial process used for making ammonia is called Haber-Bosch process. In this process, the pressure and temperature are kept extremely high. Maintaining such conditions requires enormous amount of energy. This process also contributes to 2 to 3% of the world's total carbon dioxide emission. But the nitrogen fixation can also be done by an enzyme called nitrogenase. The enzyme nitrogenase is produced by prokaryotic microorganisms, and most of the ammonia in nature is produced this way. The enzyme nitrogenases is successfully able to break nitrogen-nitrogen bond without consuming any large amount of energy and causing any pollution. The only problem is that the mechanism of this reaction is not well understood. Quantum simulation could help in understanding the reaction more precisely by simulating it. Quantum simulation could help in electrical power transmission. As of today, we mainly use materials like copper and aluminium for electrical power transmission. These materials are good conductor of electricity, but they do offer electrical resistance up to some extent. Due to this electrical resistance, on average we lose around 8 to 15% of the power while transmission. But the materials, for example superconductor, offer zero electrical resistance, but they exhibit such a property at an extremely low temperature. The temperature for superconductivity is generally below -53 degrees Celsius or 20 Kelvin. Quantum simulation could help build superconductors that would work at normal to high temperatures. If we could be able to build high-temperature superconductors successfully, then the electricity will be able to transmit it without any power loss, regardless of the distance. So these were the problems in which quantum computer might get that quantum speed up. But now you may ask that, which is the superior form of computing? I would say neither of the two. Both are best at doing their own jobs. The quantum computer might only be good for solving some specific problems, while for most of the daily tasks classical computer is the best option. Now that I have talked about the problems that a fully fault-tolerant quantum computer might be able to solve, let's discuss the challenges in making such a quantum computer. There are various challenges in making a fault-tolerant quantum computer, but I am going to talk about the three major challenges. And if you don't know what a fault-tolerant quantum computer is, it is an ideal quantum computer, which is immune to any type of errors in its calculation. The first major challenge is the quantum decoherence. It can be considered as the loss of quantum information over time due to the unwanted interaction of quantum particles with its environment. You can relate it to as the energy loss of something over time due to friction, caused by its interaction with the environment. As the quantum decoherence causes the loss of quantum information, and loss of quantum information contributes to loss of the quantum properties of the quantum particle. So in simple words, quantum decoherence contributes in the loss of the quantum properties of the quantum particle. Quantum decoherence is a phenomenon that cannot be avoided. Rather, the time it takes for a quantum particle to get decohered can only be delayed enough so that the calculation can be performed in that time frame. But controlling the decoherence time is like balancing a pencil by its tip on the finger. Even a slightest flow of air can cause the pencil to drop down. The second major challenge is the error in the quantum information. When we store quantum information in the quantum particle, the unwanted interaction of quantum particle not only causes the loss of quantum information, but also introduces noise to the quantum information. Noise is the unwanted disturbance or change in the information. To reduce noise in the quantum information, the concept of quantum error correction codes have been developed. But noise in quantum computing can occur in various different ways in complex manner, as compared to a classical computer. That's why there are not many efficient QEC codes that can greatly reduce quantum noise, as there are classical error correction codes. QEC codes are more of a topic of research than practical use currently, so noise correction remains a big challenge in building a quantum computer. The third major challenge in building a quantum computer is the scalability of qubits. In order to increase the computational power of a quantum computer, we need to increase the number of qubits inside it. And those qubits must work in quantumly entangled pairs. And in order to do so, all the entangled pairs must be perfectly isolated from each other, to avoid interaction with the environment. But as the number of qubits increases, the chances of unwanted interaction with the environment also increases, causing the entangled pairs to decohere. So these were the major challenges that a quantum computer must overcome to become fault-tolerant. Until the quantum computer is not able to overcome these challenges, it's nothing more than just a cool topic for a nerd to talk about with his friends. If you have watched the video this far, then probably you are that nerd too. But thanks for watching, and subscribe to the channel, or this quantum computer will not be happy.